All right, we're going to take some notes on freefall motion. All right, this is the first half of what we're covering this unit. In freefall motion, what we have are objects moving under the influence of gravity only. I spelled influence wrong. That's okay. This is the important part. The only thing causing the objects to move is gravity. So when I throw an object, while it's in my hand, not free fall. When I let go, free fall. So when we're talking about gravity only, gravity is the force of the earth pulling on an object. When this happens, we get a special acceleration. We use a lowercase g for it, and it's 9.81 meters per second squared. And since the earth only pulls down, that's directed down. So any object that is either, and here are the words that we're looking for, falling or thrown, and that falling could include dropped, is going to accelerate with the acceleration due to gravity, 9.81 meters per second squared down. Now, about that number, it's 9.81, but it's really close to 10 meters per second squared. So for classroom calculations, this one's fine. It's 2%, 1.9% of 9.8. So it's not that big of a difference, and it makes classroom calculations easy because you're multiplying by 10. If you're in a laboratory setting, .8 is good. But for classroom calculations, while we're practicing these kinematic equations, we can use 10 meters per second squared. It's an estimation. It's not exact. It's not the most right thing that we could do, but it's acceptable to go ahead and use 10 meters per second for the acceleration due to gravity. So the words that we're looking for when we're talking about being in free fall motion, this happens when we... So it's going to be free fall. We get to say that the acceleration is equal to g, is equal to 10 meters per second squared down. We get to say that when we drop an object, falls, an object is released. And for now, when an object is thrown up or down. Because once it's released, once it's out of your hand, in all of these situations, we're in free fall motion. Now, solving free fall problems is no problem, because we're still going to be using those kinematic equations that we used before. We're still going to be using the guess method, but things are getting a little bit more difficult because I'm not going to tell you the acceleration. I'm going to say something like this. An object is dropped from the top of a bridge. An object is thrown straight up into the air. An object is released from rest and allowed to fall. When you see those things, when you see those words, you need to associate them with the acceleration due to gravity, 10 meters per second squared. Because when those things happen, we can say, boom, this is our acceleration. That's a known that we already have. So there are two big situations that we're going to look at here. One is a dropped object. For our dropped object, like we're going to be on a cliff and we have our object and we drop it and it's going to fall and hit. For our dropped object, for our givens, for our known information, if it says dropped, we say the acceleration is equal to g is equal to 10 meters per second squared down. The down thing is important. Direction matters, so draw your down arrows there. So the acceleration is g, 10 down. That's what happens when it says dropped. When it says dropped, we also know that the initial velocity is going to be 0. Those are the givens that we automatically know when we see the word dropped. Now, when we look at it, our delta y is going to be in the downward direction. Time doesn't have a direction, and my final velocity is going to be in the downward direction. Mathematically, in this case, everything is down, and we have no opposites as far as direction is concerned. If we say no opposites, then what we're going to do is say no negative signs. It's going to make our lives easy. So when we drop an object, everything is down. These are the givens that we have. The acceleration due to gravity is 10 meters per second squared down. The initial velocity is 0. The problem's going to have to give you one more piece of information, and then you can solve for anything you want. The other thing that we're going to look at is an object that is thrown straight up. As soon as we release this object that is thrown straight up, and we'll do a little picture of that. The object goes straight up, stops and turns around, and it comes back down. For that, I'm going to just spread out a little bit so we can see what was going on. For that object thrown straight up, right away, our givens know that the acceleration is equal to g is equal to 10 meters per second squared down. We know that right away. That's one given that we have. But that's the only every single time given. This is the only one that is, I guess, true at all points for an object that's thrown straight up. But when we look at it, the initial velocity is up. These two things disagree in sign. Because they disagree in sign, now we have to make the acceleration due to gravity negative, because that disagreement has to have a mathematical designation. Mathematically, the way I say that the acceleration is opposite the velocity is to give that acceleration a negative number. That's a really, really important part of an object thrown straight up. Now, for this object thrown straight up, the initial velocity is the same for the whole problem. But there are two special places that we can look at. One is the top. At the top, I get a nice piece of given information, because at the top my object stops and turns around. The final velocity at the top is 0. This is also known as the maximum height. So if we ask about the object at the top of its trajectory, or if we ask about the maximum height of an object, the final velocity at the top is 0, and that's where the maximum height can be found. The other place that we're going to worry about is when we return to launch height. In this case, the delta y is our piece of given information, and it's equal to 0. When we return to our launch height, we've made a round trip. And so because of that, our displacement is 0 in the y direction. That's a piece of given information for me. These are really, really important. The next thing we're going to talk about is a conceptual thing of what's happening at the top. So at the top of the trajectory, here's what we know happens. The object is going to turn around because on the way up, we were moving up but slowing down. And then at the top, the object stops temporarily and turns around. And then on the way down, the object speeds up and moves down. But each one of these three places is acceleration. Because slowing down is a kind of acceleration. Turning around is also a kind of acceleration. Anytime a moving object changes direction, it experiences acceleration. So at the very top, we have acceleration. And then at the bottom, we also are accelerating. Because we're speeding up. And in each one of these cases, we're accelerating in the downward direction. On the way up, we're moving up but slowing down. So the acceleration is down. At the very top, we're going from moving up to moving down. We're changing our direction in the negative direction. And then at the bottom, we're moving down and speeding up. In all of these cases, the acceleration is down. The acceleration of the object is down on the way up. The acceleration of the object is down at the very top when we stop and turn around. And the acceleration of the object is down on the way down when it is speeding up in the negative direction. So we're going to do some practice with these kind of free fall problems. But we're really just adding one extra layer to the guess method and solving these kinematic equations, that extra layer being acceleration due to gravity and those special points along our path.